This is Premier Aerodynamics Podcast number 27, and today we're talking about the aerodynamics of a cheetah tail. So that's right, a cheetah tail. I've never thought about this, but I came across this paper, which is really cool. It's called Quasi-Steady State Aerodynamics of the Cheetah's Tail. And the reason why a cheetah's tail is actually contributing to the aerodynamics of a cheetah is because a cheetah runs so fast. And what they conclude from this study is that, yeah, a cheetah tail does actually help a cheetah dramatically change directions, accelerate and decelerate depending on its orientation. So it can whip the tail around and change direction, or it can lower it or put it up higher. And for something that seems so simple, it's actually very complex. And we'll go through the details here as to how it works and why. So this paper is open access. You can get it in the link in the description. And moving on to the abstract. So they say, during high-speed pursuit of prey, the cheetah has been observed to swing its tail while maneuvering. Now, typically, researchers have considered that this is mainly just for inertial effects. So when you whip around something that's going to help orientate yourself a little bit differently, just through inertia. But this paper has actually found that it's also aerodynamics as well, and arguably even more perhaps. They also say in the abstract that the fur nearly doubles the effective frontal area of the tail without much mass penalty. And that right there is a dead giveaway that it is something to do with aerodynamics, because when it comes to moving direction, you don't really want to have so much mass away from your center of gravity. The more mass you have away from your center of gravity, the harder it is to turn. You have a high second moment of inertia, and then you need more torque to turn the same amount at the same rate. So having a greater frontal area, you can then increase the aerodynamic forces on the object without much of a mass penalty. So then you can still get that aerodynamic advantage without those inertial disadvantages. Moving on to the paper, they say that during pursuit of prey, the tail is swung from one side of the body to the other for the initiation at high speeds, for turn initiation at high speeds. And it can go upwards and downwards during rapid acceleration and braking maneuvers. Now, they say later in the paper that apparently the average hunting speed of a cheetah is about 20 meters per second, so about 70 kilometers per hour, about 45 miles per hour. So that's high enough for aerodynamics to start playing a factor, especially if you have a tail with a fairly large frontal area. Measurements of cheetah tails, however, indicate that the tail is relatively light, and as most of its mass is located near the base, the relative moment of inertia is modest. So this is what I was talking about earlier, where because you have a light tail, you don't get that inertial penalty. If you had a heavier tail, you'd have a lot more mass away from the center of gravity, which would actually make it much harder for the animal to turn. What it would need is much stronger muscles to be able to swing this tail as quickly, to then be able to turn as quickly. So by having it light, you can then just get those aerodynamic advantages without those inertial disadvantages. The aerodynamic effects of the cheetah tail during rapid movements have not been investigated, and our hypothesis is that the long furry tail generates aerodynamic forces. And to do that, they looked into wind tunnel measurements, and the results in discussion, I won't go through the wind tunnel measurements because you can look at that if you like. If you like with the method, it's fairly straightforward. With the results in discussion, they say that the effective area in the midsection of both tails, so they had two cheetah tails just for good measure, one from a male, one from a female, slightly similar ages, and one was a bit heavier than the other. But they found that with both of these tails, the effective area is almost double the frontal area of the tail without fur. So without fur, it was a certain frontal area. With fur, it was 1.8 times the amount, allowing an increase in aerodynamic forces without significant mass penalty. The final drag coefficient data with effective areas determined above are depicted in Figure 1b. So in Figure 1b, for those of you listening, it have all these tails at different Reynolds numbers, and they're actually incredibly draggy. So the drag coefficient ranges at minimum 1 up to 1.4. So that's very draggy, which means that you're going to be getting a lot of force from sticking the tail up. They also have a picture of a cheetah running through a paddock effectively at different velocities, and the tail is at different orientations depending on the velocity. So that's quite amazing. Or different parts in the stride as well, it seems. So they go on and say During the wind tunnel measurements, we observed that the very long fur on the tail tip tended to collapse at high airspeed, so above 20 meters per second. But this deformation of the tip fur was not observed in the video footage of cheetahs performing rapid maneuvers. So they took videos of cheetahs, and in this figure, they have a few frames of it. And interestingly, the fur on the top of the tail doesn't collapse. So they can even control, it seems, the fur on the tip of the tail to maximize the frontal area, which will then increase the aerodynamic drag. They go on and say this implies that the tail may potentially exert even greater forces on the body than they have estimated because a greater frontal area. They then go on and say the aerodynamic effects make a contribution to the angular impulse. In the pitch, roll, and yaw cases, and these are 26%, 12.6%, and 28% of the total 30 meters per second. So they have a very big effect on the change in direction in the three orthogonal moment directions. Initially, the effect of the tail is inertial, but as the inertial effects decrease, the total torque is maintained by an increase in the aerodynamic torque. Tail motion in the pitch axis has been attributed to both increasing pitch stability and lowering the peak forces on the front legs. So that's pretty amazing. This tail not only helps with changing the orientation of the animal, it can also reduce the peak forces on the front legs. Pretty amazing. In addition, by yawing the tail in the aerial phase, the cheetah can redirect its body heading, and by rolling the tail, it can bank the body appropriately into a turn or counteract the destabilizing effect of the centrifugal force. So if they're running in a curve, there's going to be a centrifugal force. They can whip their tail around and use aerodynamics to counteract that. In all cases, the aerodynamic force also has a braking effect. So it can also decelerate the animal as well. So they can not only accelerate very quickly, but decelerate very quickly as well. So that's the end of this podcast. It was a bit of a short one, but I found this really amazing that the cheetah tail has such an effect on aerodynamics. You never think about that, but considering how fast it moves, it makes sense. So make sure to like and subscribe to this. Check out everything we do here at Premier Aerodynamics. Check out the instrumentation we do. We make an atmosphere hawk, we make PIV systems, we make traverses. Check out the courses we put on to make you a better aerodynamicist. We have theoretical, experimental, and CFD. And check out the International Premier Aerodynamics Conference. It's a conference every year we put on for aerodynamicists to get together and talk about aerodynamics. See you in the next podcast. Peace out.